We now have S-domain models for R, L, and C. The next question is, once the circuit is transformed, do we need new circuit laws? No, Kirchhoff's current law and voltage law still apply. We simply write them using Laplace domain currents and voltages. The only new pieces are the initial condition source terms. Today we write one node equation and one mesh equation directly in S. Start with node analysis. Pick the reference node, then define the unknown node voltage V of S. For every branch leaving the node, write the branch current using the S-domain element model. A resistor to ground gives V over R. A capacitor to ground with initial voltage V0 at the top plate gives IC of S equals SCV of S minus CV0. That minus term is the memory term. If we move it to the source side, it becomes plus CV0. Here is the node example. A current source IS of S injects current into the node. A resistor and a capacitor go from the node to ground. The capacitor starts with voltage V0. KCL says input current equals resistor current plus capacitor current. So IS of S equals V over R plus SCV minus CV0. Collecting the unknown V gives, open parentheses, 1 over R plus SC close parentheses, V equals IS plus CV0. Two quick checks make the equation trustworthy. If the initial voltage V0 is 0, the memory term disappears and only the input source drives the node. If the input source is 0, the stored capacitor energy still drives the natural response. The same equation gives V of S equals V0 over S plus 1 over RC. So forced response and natural response live together in the same algebra. Now use mesh analysis. Pick a loop current I of S and traverse the loop. Every S-domain branch contributes a voltage drop. A resistor gives Ri. An inductor whose current reference matches the loop gives SLI minus Li0. KVL says the applied source equals the sum of drops. The sign of the initial source is not something to memorize first. It comes from the chosen reference direction and the transformed element law. For the mesh example, take a series voltage source Vs of S, a resistor R, and an inductor L. The initial inductor current I0 points in the mesh direction. KVL gives Vs equals Ri plus SLI minus Li0. Collecting I gives, open parenthesis, R plus SL, close parenthesis I, equals Vs plus Li0. Therefore, I of S equals Vs plus Li0 divided by R plus SL. The general workflow is mechanical. First, transform independent sources and all R, L, C branches into S-domain models. Second, keep every 0 minus initial condition. Third, write KCL or KVL exactly as you would in circuit analysis. Fourth, collect the unknown node voltages or mesh currents. Fifth, solve in algebra and inverse transform if you need the time waveform. For larger circuits, the same process becomes a matrix equation in S. Watch for 5 traps. Do not use 0 plus when the element model needs 0 minus. Do not give the memory source the wrong sign. Do not forget that independent sources also transform into the S-domain. Do not mix time domain elements with S-domain equations. And do not drop natural terms just because the external source is 0. Stored energy can be the source. Summary. Lesson 17 gave us the branch models. This lesson shows how to use them in equations. Node analysis collects admittances around V of S. Mesh analysis collects impedances around I of S. The result contains the input response and the initial condition response together. Next, we turn these equations into transfer functions, output over input, with 0 initial conditions.